And yeah, good morning, everybody. Thanks for joining us. So, what I want to talk about is some of the recent work that we've been doing in our group on basically analyzing neural networks, and in particular, analyzing and trying to understand what they learn from their data. And so, I want to share some of those results. And since this is a Zoom talk, I think it's particularly important. You know, if you have a question during the talk, just speak up. I'm not sure I'm going to see you if you raise your hand. So yeah, if you have a question, just speak up, and let's try to make this as interactive as possible. So yeah, so again, thank you, Tiffany, for the invitation, and let me jump right in. So, what my group is interested in is really the story of what do neural networks actually learn from their data, right? So, what kind of statistical structures, what kind of patterns do they extract to then do their task? And so, this is really a question about feature learning, and it's been really part of yeah, neural networks since the very beginning, right? And I don't want to get into any sort of historical arguments, but I think one beginning for deep learning was certainly the AlexNet paper, right? When Krzyzewski, Sutskever, and Hinton trained this deep convolutional neural network to achieve the state of the art on the ImageNet classification challenge. And if you look at that paper, it's actually quite an interesting read. You can see some discussion of ReLU, you can see some discussion of how they split the training on two GPUs. But then at the end of the training, of the paper, sorry, they also show what the network learned at the end of training, okay? And in particular, they show the filters, the convolutional filters in the first layer of the neural network at the end of training, okay? And this is the plot taken from that paper. And if you're a computer vision person, or if you're like a theoretical neuroscientist, it's pretty exciting to you because you know these guys, right? So these are Gabor filters. So the interesting observation here at the end of the paper was that this particular combination of a rich data set, of a convolutional neural network architecture, and gradient descent as a training algorithm yielded something that looks approximately like a Gabor filter, which we know is, you know, for all kinds of reasons, a useful and appropriate filter for images. But the approximate sign is important, right? Because if you now think that you could actually bypass the training and you could just replace this first convolutional layer with the mathematical definition of Gabor filters, you'll actually perform worse. Okay. So there is actually something here in the data that the neural network picks up, and that's really important to its performance. And to me, this is one of the first examples of this lesson that we've now learned over and over again in deep learning, that the data-dependent features, so the features that you learn directly from the raw data, usually perform much, much better than the features that we would handcraft with all the domain knowledge and all the sort of physical intuitions that we might have. Okay. And so what I want to understand is sort of what is it in the data that these neural networks actually pick up here. And similar ideas appear also in neuroscience, right? There's this idea of efficient coding. In other words, that the receptive fields, for example, in the visual system, are somehow tuned or adapted at least to the statistics of the environment in which you grow up. But here for this talk, also for this audience, I'm going to try to focus more on the mathematical aspect of this idea in the machine learning context. Now, if you want to analyze what you learn from data, you need some kind of model for the data, right? So you need some kind of structural assumptions on the data to make the representation that the neural network learns interpretable. Okay. Now, there's different approaches to this idea. I myself come from statistical physics, and there's a long sort of history in statistical physics of analyzing neural networks using the tools of disordered systems. And there, what people usually use is the so-called teacher-student setup, right? So the idea here is that you have a data set that consists of IID Gaussian inputs, and the label of these inputs is given by some random teacher network. Okay, random in the sense that the weights are random and fixed. And then, you know, you sample inputs, you propagate them through the network, and that's how you get your labels. In statistical physics, we like to trace this idea back to this famous paper from Gardner and Derrida, but of course, you know, this community is not the only one who works in this kind of setting. This is what what statisticians would call the Gaussian design. Or, you know, you could talk about just learning a target function. Of course, this is very nice because, you know, it gives you a lot of structure in the task, but doesn't give you any structure in the inputs, right? Here I'm showing you a sample of such an IID Gaussian vector. It's just noise, right? Now, more recently, yeah. So all the complexity of the task is in the target and the teacher function. Now, more recently, there's been some work on extending this kind of theoretical approach through to correlated inputs, to more realistic inputs. And the keyword here is this idea of Gaussian equivalence, right? So in many cases, we can hide away a complex data set behind an appropriately chosen Gaussian model for the data. So main Montanari observed this for random features. We did some work on this in the context of neural networks, and this has spawned sort of a whole series of works, and we've learned quite a lot, I think, from this approach. But this is still only a poor model of data, right? This is still ignoring all the higher order correlations in the inputs. And these higher order correlations, they're important. Okay, so here, for example, I'm showing you the test accuracy at the end of training for some deep sort of off-the-shelf convolutional neural networks, okay? And I'm showing you them when trained on Cypher 10. These are the red bars. And when training on a Gaussian mixture that's been fitted to Cypher 10. These are the green bars. And you can see that there's a huge gap, right? So the DenseNet, for example, its performance drops from something like 90% test accuracy to only 25% or something like that. So there's lots of information that the neural networks extract, maybe unsurprisingly, from higher order correlations. But these theoretical approaches that I discussed so far, they can't capture that, right? They cannot capture the impact of these higher order correlations because they somehow assume, sometimes explicitly, sometimes more implicitly, a Gaussian model for the data. And so what I want to do today is discuss some like first step that we've done to kind of go into this non-Gaussian regime. That's the motivation. Are there any questions on this? There's also some drilling here in the background. I don't know what's going on, but I hope it's not too bad online. Okay, I don't see any immediate questions, but like I said in the beginning, right? If you have any questions, just feel free to speak up.
I don't think there's any background noise, so don't worry about it.
Okay, great, great. Then Zoom is doing some really good filtering. I'm impressed. All right. So let's jump right in. So the first observation that we made when we started thinking about this, and this is from a recent paper that we presented at ICML, is that actually there's some ordering to how the neural network scoops up these higher order correlations, okay? So here I'm now showing you one of the experiments of the previous bar plot, but dynamically. Sort of now I'm showing the test accuracy of one of those deep convolutional networks, a DenseNet here, over the training time, okay? And so you can see in violet, the test accuracy of the network that's been trained on Cypher 10. And in green, I'm showing you the test accuracy of the DenseNet that's been trained on a Gaussian mixture fitted to Cypher 10. Okay, so I'm fitting here one Gaussian for each class. So I'm fitting one Gaussian, for example, to all the horse images in Cypher 10. And then I'm sampling a new data set from that Gaussian mixture. I can train on that data set, okay? But then I'm testing on the actual Cypher 10 test set. So in other words, I'm testing how much do you learn about actual Cypher 10 images if you only look at the first 2 moments of the class conditional distribution. And you can see 2 things in this plot. So one is, of course, there is a big gap, right? So at the end of training, there's a lot more that you can learn from the true Cypher 10 training set than what you can learn from the Gaussian mixture. But what to me was very striking is that in the beginning of training, so here for the first 10, 20 steps of SGD, it actually doesn't make a difference whether you train on the Gaussian distribution or on the actual images, right? So here for the first 10, 20 minutes, the test accuracy of these 2 networks, even though they're trained on very different distributions, it's actually the same. And so to us, this meant that in the beginning of training, the neural network actually only looks at sort of the mean and the covariance of each of the classes in the training data set, okay? And then, okay, we wanted to see what happens after that, right? So what happens after you go beyond the Gaussian model? And ideally, what we would like to do is sort of cleanly interpolate training sets, right? Sort of construct in a principled way increasingly accurate approximations of the Cypher 10 training set, where maybe you would have the first 4 cumulants turned on and the rest of them 0, something like that. But unfortunately, you can't do that. So there's a theorem that tells you that as soon as a data distribution has a non-trivial third order cumulant, all of the cumulants are non-zero. Okay, so it's kind of hard to extend this idea of a Gaussian approximation where you just have the first 2 cumulants and the rest are 0. But what you can do if you're a deep learner, you can just use a neural network, a generative neural network, and train that on Cypher 10. So that's what we did. So we took an ensemble of GANs, Wasserstein GANs to be precise. We trained them each GAN on one of the classes of Cypher 10, and we sampled a new data set from those images. And you can see that this gives you a better approximation of the true data set, right? So just visually, these images look much closer to Cypher 10 images. Here, this actually looks a little bit like a horse, a little bit maybe like a frog. And you can also see that if I train on this data set, I perform much better on the actual Cypher 10 test set, Okay, so you can see that the asymptotic value of this WGAN trained network, it's much higher. But what's again striking to me here is that for the first now, let's say 1,000 steps of SGD, the two curves collapse, right? So for the first 1,000 steps, as far as the test accuracy of the network is concerned, it doesn't make any difference whether you're training on Cypher 10 images or the Wasserstein-Gunn generated images, right? So all of the sort of higher order information that's contained in Cypher 10, it doesn't matter up until that point. And you can play that game with more complex generative models, right? So here I took some samples from the Cypher 5 million dataset. This was sampled from a big diffusion model by Preetam Nakiran for a paper a couple of years ago. And you can see same story, right? So better images, higher test accuracy, and for an even longer amount of time, the two curves actually collapse on top of each other. So in other words, there is some ordering here, right? So neural networks kind of seem to be learning about their data distribution in an ordered way. They seem to be learning distributions of increasing complexity here through time, okay? And this is nice because this gives us also some ordering to then do some theory, okay? I'll show that in a second. For now, let me just say, so this works on different architectures. We also tried this on the visual transformer, on some ResNets. But what I find interesting is that this also works on pre-trained neural networks, okay? So if you think about it for a second, you could say, well, at the beginning of training, the weights of my neural networks, they are IID drawn from some from some probability distribution, right? So if you hit the image with such a random filter, there's some strong central limit theorem kind of vibes going on. And this is why in the beginning, the data looks approximately Gaussian. So what we did here is we repeated the same experiment, so same pipeline, same data sets, same protocol, everything is the same. But the network that we took was not randomly initialized, it was pre-trained on ImageNet. Okay? And then we just sort of train the whole network end to end again on these different data sets. And you get the curve that I'm showing you here on the right. And so you can see that the pre-training actually speeds up learning. Okay? So before it took you maybe 1,000 steps to get to 60% test accuracy, now it takes you only 100 steps. So pre-training has an effect. But as far as sort of the trajectory of learning is concerned, the plot looks very similar. Right? So in other words, the neural networks goes through the same motions, first learning roughly a Gaussian model, and then going through these increasingly accurate approximations of your training data set. So I think this is quite interesting because it also raises some questions about, some of the maybe a bit anthropomorphic intuitions that we have about pre-training, right? That you learn some concepts that can then be translated to a new data set. Maybe it's just about the optimization. Maybe it's just about finding a good initial value for your weights that speed up training. I don't know. But yeah, in any case, this learning of distributions of increasing complexity, it's robust also to these non-random initializations. And then finally, we're also finding similar behavior in transformers. So here, I'm going to focus for the rest of the talk on fully connected networks because we want to do some theory, but just to show you that also in a sort of vanilla Roberta-style transformer, you can play the same game now on masked language modeling. In blue, I'm showing you the test error of a transformer that's been trained on Wikitext, which is just one of these openly available text datasets on which you can train to predict the next token. And in green and in yellow, I'm showing you the test accuracy of the same network, but evaluated on a sort of 3-body energy-based model that we fitted to Wikitext, and a 4-body energy-based model that we fitted to Wikitext, right? So in other words, these are approximations of Wikitext that only have up to 3 or 4-body interactions in the data. And you can see that for quite a bit of training, for the first, let's say, 20 epochs, it doesn't really make a difference. The transformer doesn't really see any of the correlations that go beyond 4-body interactions. And only later in training, you see that the blue line sort of goes away and separates from the green and orange. And you can also reduce this on simpler models of data. Here's a simplified transformer on some synthetic data sampled from a Gibbs model, and we see the same sort of sequential learning.
Будет мешать, если на фоне будет вот это. Ну, то есть не тут на фоне, а в другом. Я просто записываю.
Sorry, can you repeat that?
Sorry about that. Sorry.
That wasn't a question.
No, it was not my bad. I did not realize I was not muted. I apologize for
Okay,
that.
okay. Okay, no worries, no worries. So yeah, so I think, so what I'm trying to say here is basically that this is a phenomenon that doesn't just occur in computer vision, in classification, it also occurs in transformers, which are very different architecture, and on text, which is a very different type of data. So I think this might be a fairly general phenomenon, and we're currently exploring a little bit the implications of that. How can we analyze that now? So let's go away from these big models and go to the simplest model that we can possibly think of, which is just a single neuron, right? Just a single perceptron. And we can see a similar behavior also in a very simple data model when training a perceptron. So here the data model is essentially a binary classification task. You have high-dimensional inputs, and if I plot those inputs, along their two principal components, if you will, the two leading principal components, you can see that the inputs nicely cluster. Okay, you have red dots in one class, yellow in the other, and they are sort of drawn uniformly from this rectangular support in input space, right? And you can think that all the other dimensions are just random noise. So here your task consists of first finding the subspace and then finding this oracle separation, this perfect linear classifier that separates these two classes. Like I said, we looked at this with just a single neuron, because then we can analyze the learning dynamics in quite some detail. We looked at the dynamics of gradient flow. Nothing particular here. We just fix some loss. It's not so important whether we use mean squared or cross entropy, because what we're going to do is we're just going to expand that loss later. And if you do that experiment, okay, you see that the test accuracy, actually this is the test error, sorry, goes down through time, and it has sort of this prototypical shape of some exponential decay in the beginning, some slowdown plateau in the middle, and then another exponential decay at the end. And what you can do here is, if you do this expansion and you sort of look at different learning times for the perceptron, what's nice in this model is that you can see that it will learn different classifiers, and those different classifiers will be increasingly accurate, and they will take increasingly higher order of the data into account. Okay, so if I just look at this dynamics of gradient flow up to 0th order in the weights, okay, I can just write it down. And then I see that, at least in direction, my weights are converging, and the direction in which they're converging is shown by this yellow line here on the plot, on the data plot, okay? So basically here I'm learning a very simple classifier, we call it the naive classifier, which is just looking at the means of the inputs in each class, okay? And then basically drawing a line between the two, okay? So this classifier really just takes into account the mean of each class, and that's it. So as you can see, it's suboptimal, right? Because it cuts off quite a bit of the support of these data distributions, right? It has quite a bit of an angle to the oracle, which is this black line. If I now let the training run for a little longer, right, I have to include one more term in my expansion of the gradient flow. And what I find is that now I'm learning a classifier that actually performs a bit better, okay? And it performs a bit better because it exploits information from the second order correlations of the inputs. Okay, and in particular, it uses a sort of within class covariance between the inputs. In neuroscience, you would call these the noise correlations, actually, of the inputs. And you basically use this correlation matrix to rotate the naive classifier. And if you do the computation, you see that you actually rotate it in the right direction. So you get closer to the oracle, you perform better. And this form of a classifier is actually well known in statistics. It's just a linear discriminant or a Fisher discriminant. And this is what you get if you just include the first two moments of your data, if you essentially assume a Gaussian model. And then if you're a bit more, if you want to do a bit more work, you can actually also compute the first non-Gaussian correction here, which gives you a classifier that looks like that. And this one, again, now exploits the non-Gaussian correlation. So this exploits now the cumulants of the higher order cumulants of this data distributions, which are non-zero because this is not a Gaussian mixture. And again, sort of what this gradient flow also nicely shows you, we can discuss afterwards, is basically which of the higher order correlations are important, right? So some of them don't help the classifier, but some of them do. And in this case, it's again this sort of within class cumulant, which is a generalization of noise correlations to higher order modes. If you flip this around from a complementary point of view, what this means is that you can expand the gradient flow over time, or equivalently, you can just say, in the beginning, my perceptron behaves as if my data was drawn from a Gaussian distribution, which has the correct means and isotropic covariance. Okay, so here I'm basically replacing my true data distribution, the dots, with a new data distribution, which is the effective distribution that my perceptron sees in the beginning of training. Okay, and this would be this Gaussian isotropic distribution. And indeed, if I train the perceptron on this Gaussian isotropic distribution, I get this yellow line for the test accuracy, and they coincide. So my train accuracy on this clone and my test accuracy on the true data, they coincide in the beginning of training. In the beginning of training, this is what the data looks like to my perceptron. And then later on in training, you get the idea now, I can replace this with an anisotropic Gaussian taking into account second correlations, and then also, finally, I see the higher order cumulants. So the takeaway of this first part is that, okay, neural networks really rely on these higher order correlations to perform their tasks. And they seem to be learning about those higher order correlations in some kind of ordered way, right? There seems to be some kind of ordering to how the neural network sweeps up those higher order correlations. It seems to be learning effective distributions of its data, which get increasingly more complex. And we can see this sort of in the real data, in the experiments with deep networks, and in these toy models with perceptrons trained on static data sets. So this is sort of the first part of my talk, and so maybe this is a good point to pause again and ask if there's any questions.
I would have a question.
Yes.
Yeah, so really interesting stuff. So I was wondering how this might relate to learning rate decay, where initial large learning rate is also thought to like affect what the order of learning is.
Yeah, that's a good question. So I haven't thought so much about like learning rate schedule. What I can tell you is that in these experiments, for example, with the with Cypher 10, with the deep convolutional neural networks, there we have some pretty standard learning rate scheduling. I think it's some kind of step schedule. So after each, I don't know, 10 epochs, you reduce the learning rate by, let's say, factor of, I don't know, 0.5 or 0.1 or something like that. I guess some people have observed this sort of catapult phase, that you have these big learning rates in the beginning, you get away from your initial point very quickly, and then you decay, and then you actually start learning. Maybe here this would translate into breaking out of this Gaussian regime very quickly, but I don't know. That's a good question.
Okay, thank you.
Any other questions at this point? Okay, so yeah, then let's go to the second part. And so, if, and this is kind of what I've been trying to argue here, that higher order correlations are so important for neural networks, then you should ask, and how efficiently do they actually learn from them, right? If they are important in your data, you want the machine learning method that is actually efficient at extracting information from them. Okay, and so we looked at this in this project here, where we basically thought about learning higher order cumulants as a hypothesis test. Okay, so the idea here is that if I want to know, how quickly does my neural network access the higher order correlations in its data, what I can do is I can basically set up a very simple classification task, a binary classification task, where I have some images, for example, the horse images in Cypher 10 on the one hand, and I'm trying to discriminate those from Gaussian inputs, which have the same mean and covariance, right? And as soon as the neural network is able to do this task, I know, it extracted some information from the higher order cumulants, right? Because that's the only way you can do this task, right? If the inputs have the same mean and covariance, the first sort of discriminatory statistic will be the third or fourth order cumulant. Now, this is, of course, nothing but a hypothesis test, right? So I'm really sorry. I'm really having a null hypothesis here, Q, which is just a Gaussian with some non-trivial mean covariance. And then I want to see whether my data follows this null hypothesis or whether it follows the law of my alternative model, which here would be P, so the planted model. Now, of course, analyzing this kind of hypothesis test mathematically with images is a bit hard. So what we did is we came up with this slightly simpler model for data to kind of capture this idea, okay? And we call that the spiked cumulant model, okay? So under Q, under the null hypothesis, you basically observe a data matrix X, which is, inputs, number of inputs times input dimension. And each element of the data matrix is just IID drawn from standard Gaussian distribution. Okay, this is your null model. Now, under P, instead, you observe data which has the same mean, 0, the same covariance, identity, but third order cumulant here is 0 for some symmetry reasons, but then the fourth order cumulant under P is different from the fourth order cumulant under Q. Okay, so how do we do that? We do this in two steps. So first, you generate a particular input, so an input vector x tilde now, like this. So you fix a spike direction, which you're going to call u. This is drawn from some prior distribution. You could just take it element-wise plus or minus 1, something like that. Okay, and then each input will be a sum between a signal-to-noise ratio beta times a scalar random variable. We're going to draw this Rademacher here. times the spike plus a Gaussian noise vector. Okay, so W is again element-wise ID from the normal distribution. You've probably seen a model like this before, right? So if I take G to be a standard Gaussian distribution, this would give me back the standard Wishart model of random matrix theory, right? So these inputs would be Gaussian, they would have zero mean, and they would have a covariance, which is the identity plus beta UU transpose. Now here instead, if I make my G non-Gaussian, if I draw it, for example, from the Rademacher distribution, my X become non-Gaussian, but I could still easily detect that there's something, I could still easily distinguish this distribution from my null hypothesis, Q, because the covariance is still non-trivial, right? So what I need to do here in the second step, and this is really crucial, is I need to whiten my inputs. Okay, so in this case, I can actually compute, I can actually compute this whitening matrix analytically. And so my final inputs, X, will be the product of this whitening matrix times X tilde. And in this way, I will have inputs which have zero mean, identity covariance, zero third order cumulant for symmetry reasons again, but a fourth order cumulant which will be proportional to the outer product of U to the fourth. Okay. And so now I can ask, okay, how much data, for example, do I need to distinguish these two distributions? And this is something that we did with Lorenzo Bardone, who's a PhD student here at CISA. And essentially, we looked at this in the typical high dimensional limit. Okay, so we have the input dimension D and the number of samples that go to infinity at the same time. And we look at basically a polynomial scaling between the two, right? So N is proportional to, or asymptotically grows as D to the theta. And then we have some technical conditions, but essentially what we show is a theorem that tells you that if theta is less than 2, so in other words, if you have less than quadratic sample complexity, if your number of samples grows slower than quadratically in the input dimension, then no algorithm can distinguish P and Q in a time that's polynomial in D. So in other words, there's no efficient algorithm, computationally efficient algorithm, that is able to detect the non-Gaussianity in your data. Okay? You need at least a number of samples that's quadratic in the input dimension. And when I say no algorithm here, what I really mean is no algorithm from this class of algorithms that can be approximated using degree D polynomials. For those of you who maybe have heard of this method, I'm basically using tools from low degree method here, the low degree likelihood ratio in particular. And so if I let the degree of those polynomials grow logarithmically, like I have it here on the slide, I'm also including things like spectral algorithms and all that kind of stuff. Okay. So again, if I wanted to do PCA on a spiked Wishart model here, I would just need linear amount of samples. Okay, I could solve this problem with a number of samples that's linear in the input dimension. But here, for the spiked cumulant model, where my first sort of non-trivial statistical information is in the fourth order cumulant, I need at least quadratic sample complexity. Are there any questions on this result? Right, what I want to know now is, okay, how efficient do neural networks actually extract higher order correlations from my data? When I mean efficient, I mean how much data do they actually need? Okay, and the way I'm formulating this here is as a hypothesis testing problem, right? I'm saying you can only extract information from the non-Gaussian correlations if you realize that your data is non-Gaussian, right? This is kind of a proxy task. Now I'm telling you that in this particular model of data, in this spiked cumulant model, you need at least a number of samples that's quadratic in the input dimension for any kind of algorithm, for a very wide class of algorithm. Now this essentially gives me a benchmark, right? This gives me a baseline. And now I can compare neural networks, for example, to this baseline. I can also compare neural networks. Another sort of natural comparison here would be kernel methods, right? I can ask, okay, how efficiently do neural networks now extract higher order correlations from their data compared to these sort of really fundamental statistical and computational bounds, which come from computational complexity theory? And how efficiently do they extract this information compared to kernel methods, random features, linearized neural network, right? Many of you will have seen that there's large literature in these last couple of years trying to understand what neural networks can learn efficiently that kernels cannot. So these are the two questions that we're going to ask now. And we asked those two questions with Esther, who's also here at CISA. And so we did some numerical experiments, okay, in which we looked at this spiked cumulant model that I just described to you, right? And we looked at the performance of neural networks and random features on this hypothesis testing task. okay? And indeed, what we found is that if you have linear sample complexity, so if, according to this previous theorem, you don't have enough data to solve this task, indeed, there's no magic, right? Neural networks and random features, they cannot solve this task. In this binary classification task, right, image versus Gaussian, they hit 50% test accuracy, which means they're just randomly guessing. So they don't learn anything. If I now crank up the number of samples, okay, if I now give you a number of samples that's quadratic in the input dimension, my neural networks actually start to be pretty good, right? So they detect the non-Gaussianity here. They reach a test accuracy, or test error here, which is not 0, but okay, clearly it's bounded away from 0.5. So they've picked up the structure in this data set. The random features, on the other hand, so the orange and red line here for 2 different input dimensions, they still don't do anything. And this actually makes sense if you think about it, because we know now from a nice series of works that I think I have on the next slide, exactly. Oh, no, wait. Yeah. We know that, random features do learn polynomial approximations of their target functions. And the degree of this polynomial approximation, it's determined by the amount of data that they have, right? So very roughly speaking, if you have quadratic number of samples, this means that you can only approximate your target function with an order 2 polynomial. But here, the LDLR analysis of the previous slide, it tells you that actually to distinguish these two distributions, you need an order 4 polynomial. So in other words, the target function that you're trying to learn here has order 4. It's a polynomial of 4th order. And so this means that random features in this sample complexity regime will not be able to learn it. They would need a number of samples that's quartic in the input dimension. Okay. So in other words, there's a huge separation here between what you can learn with neural networks and what you can learn with random features. And this is a bit reminiscent of other hierarchies that regarding the sample complexities that people have seen. Okay, so mostly in supervised learning, there's been a really nice series of works recently where people have shown how good of an approximation of your target function can you learn with a neural network if you do gradient descent with a perceptron, if you do one big step of gradient descent, right? And here essentially what we're showing is that if you do feature learning on a task where the task relevant information is at a certain cumulant level in the distribution, you need a certain number of samples. In this case, for the 4th order cumulant, you need quadratic sample complexity. And this means that there's a huge gap between what you can do with neural networks and what you can do with random features. But of course, there's one thing that's still open here, which is that if you think back to the plots that I had earlier, neural networks were actually able to break away from the Gaussian model of its data very quickly, right? After 10, 20, 50 steps of stochastic gradient descent, right? So there's something else going on in real data here that speeds up learning somehow. Somehow neural networks on real data set, they learn quickly about the non-Gaussian statistics. And so to do that, we need some more sophisticated models. This is something that we are working on at the moment, and I hope I'll have an update on that maybe, before the ICML deadline or something like that. But in the meantime, sort of the takeaway here is that neural networks are efficient at learning from higher order cumulants. So they are efficient in the sense that they saturate the fundamental bounds given by sort of computational complexity theory and low degree analysis in particular. And they're definitely much more efficient in the terms of data set that they need compared to things like kernel methods and random features, right? They need much less data than a kernel or random features would. Are there any questions on the second part? Let me also open my window. Okay, I don't see any immediate questions. So for the last couple of minutes, let me jump into the last part, which I think is in a sense is the most interesting, right? So we talked about the importance of higher order correlations. We saw that neural networks learn about them in a kind of ordered way, right? Learning increasingly accurate approximations of their data. And we saw that they do it in a kind of efficient way too. But the real question is, of course, what do they actually learn from them, right? So how do these cumulants actually shape the representations that a neural network learns? And this goes back to this very first plot that I showed you on my very first slide, right? So why is it that a convolutional network trained on ImageNet learns these localized, bandwidth limited Gabor filters? And so this is a question that, we're thinking about in a slightly different way. with Alessandro Ingrosso, we addressed with this very simple toy model for images. So with Ale, we were thinking about learning convolutions and learning convolutions from scratch, these kind of things. And so to study that, we wanted to have a simple model that captures some of the salient images, salient properties of images, okay? And so the two properties that we wanted to capture were the translational variance and the existence of sharp edges. So for the translation variance, what we did is we just drew samples from a Gaussian distribution with mean 0 and a covariance that has this sort of kernel that I've drawn here, where essentially the correlation between two pixels doesn't depend on where they are in the image, it only depends on their relative distance to each other, right? And so here we chose this particular exponentially decaying kernel, and then all you have to do is you have to fix a length scale xi over which these correlations decay. And if you draw a sample from this Gaussian process, you get something that looks a little bit like that. It's this typical blurry image, if you will, that you are used to from Gaussians. But if you go back to theoretical neuroscience and this kind of literature that really has thought for a long time about the salient properties of images, the statistics, one concept that's really important and it comes up a lot is the idea of images, right? So this, for example, is a paper from one of the first NURBS, I think in 96, from Bell and Zichnowsky, where they are essentially arguing that edges are really the independent components, the atoms of natural scenes, right? And edges are important. Edges just mean that there's a sudden change in luminosity, and that means that, you know, there's something like a foreground and a background that you can segmentate images, identify objects, and so on. So how do we get edges in our little model here? We just took these Gaussian vectors and we feed them through a saturating nonlinearity. In this case, you know, we took the error function because it gives you nice integrals under the Gaussian measure. And in particular, we feed it through a narrow function where we have this little scalar parameter g here. And this g, this gain, as we called it, it basically controls the slope of the error function around 0. So in other words, as I increase the gain, the slope becomes increasingly steep. And so the edges in my image, here I'm showing you examples for different values of the gain, have sharper and sharper edges. The 1 over z, that's just a normalization to make sure that the variance per pixel is the same no matter what is the gain factor, okay? And so now I really have sort of a little knob that I can turn to make the edges in my image sharper and, you know, statistically speaking, to make the inputs more non-Gaussian. And now I can actually train a neural network on this kind of data, right? So a very simple task that you can construct here is one where you distinguish images with short-range correlations from images which have long-range correlations, right? So you have a binary classification task now, and you're drawing inputs for each class from this nonlinear Gaussian process with different length scales. And if you do that experiment, we use just a vanilla feed-forward, fully connected two-layer neural network, sort of 100 hidden neurons, online SGD, nothing fancy. You can train this network, and then you can look at what did it learn, right? You can look at the representations, you can look at the weight vectors essentially of the hidden neurons in the hidden layer. And what we found was this. So the neurons split roughly into two groups, okay? Half of the neurons, the weight vectors are, we called it oscillatory, but really it's a bit all over the place, right? You can't really see any structure. I'm showing you this in this bottom row here. These are 4 neurons that I just took randomly from this group. The other half of the neurons is much more interesting in a sense, because its weight vectors or its receptive fields localize, right? So here, each sort of little pixel corresponds to one weight from one hidden neuron to one input neuron, and dark blue means very close to 0. Okay, so most of these synapses have actually died off, have been turned off, and there's only this very localized patch of weights which are large. So in other words, you learned here sort of a very simple localized receptive field. If you do some more analysis, you realize that actually these receptive fields, they tile input space, so you really get basically a convolution with a single filter from scratch, right? This is a fully connected network. There's no L1 regularization, nothing funny going on here. So this is really a data-driven effect. Data-driven because if I do the same experiment now with a Gaussian mixture, right? So this is, again, a binary classification task, but now I'm replacing the non-linear Gaussian processes, these images with edges with just Gaussians. I don't see this localization. Instead, I see these, again, high-frequency oscillations in some of the neurons, and then some more low-frequency oscillations in other neurons. And in particular, if you look at these low-frequency neurons, they are really sort of 2D superposition of Fourier components. So what the network is doing here really is PCA. Because the covariance is a circular matrix, or it's rotation invariant. And so a circular matrix, you can diagonalize that in Fourier basis. So here what the network is doing, it's doing PCA. It's finding the Fourier components which are most discriminatory for this task. Okay, so here what we wanted to understand now is, okay, what is it in the data that gives us these localized receptive fields? Okay. And so, what we wanted to understand here is essentially, if I think about the test error, for example, we want to develop a theory now for the performance of this neural network trained on the Gaussian data where there's no receptive fields, and this is the blue curve, and on the non-Gaussian data where you actually learn these receptive fields, where you learn something from the non-Gaussian data. And I don't want to go too much into detail here. So there's some statistical physics techniques that you can use here. You can use, again, some kind of Gaussian equivalence, but essentially they break down. So they break down precisely in the interesting moment when the receptive fields form. Okay, so let me just skip that in the interest of time. If you have questions later, we can discuss this more in detail. Instead, I want to show you sort of kind of what works, or what we think is going on here. Okay. So here I'm showing you now what's happening during training of this neural network. Okay. First of all, the green line at the bottom here, it shows you how localized the receptive fields are in time. Okay, I'm plotting the inverse participation ratio. It's like an empirical fourth-order cumulant of these weight vectors. And in fact, so this IPR will be 0 for a Gaussian vector, for example, and it will be very large for a very localized vector like the ones that we find at the end of training. And if you plot that now for all the neurons sort of through time, you can see that there is sort of a very precise moment in time in which these neurons localize, right? So they are kind of a mess for a long time, then they localize, and then they stay. Statistically speaking, the flip side of this is that the statistics of the pre-activations, so the statistics of the representations, hidden representations of this neural network, they change in time, okay? So in orange, I'm plotting for the same run, the excess kurtosis of these pre-activations, right? This is a measure of non-Gaussianity. It's going to be small or close to 0 in the beginning of training. It's close to 0 because the weights were initially uniform, so you don't get exactly a kurtosis of 3. But then you can see that roughly in the moment in which the weights localize, in which the IPR goes up, the non-Gaussian, the pre-activations, the hidden representation becomes very non-Gaussian, right? The kurtosis goes away from 0. And this really mirrors the localization effect of the neurons, right? So here I'm showing you the receptive fields early on in training at time t equal to roughly 10, when the IPR is low and the kurtosis is close to being Gaussian. And here I'm showing you the same neurons, but now at the end of training, right? So now kurtosis is high, IPR is high, weights have localized. Now, why I'm insisting on this thing? This could just be some kind of, idiosyncrasy of our model. After all, this is a very simple synthetic model of data, etc. But I redid the same experiment now on ImageNet with some of the architectures that I showed you on the first slide. For example, the AlexNet. Okay, so I trained AlexNet, ResNet, and DenseNet now with sort of very standard protocol on ImageNet. Okay, and then we took, so this is a collaboration with Will Redman and again Ale Ingrosso, and then we took the first layer convolutional filters, and we played the same game, right? We computed sort of what's the excess kurtosis of the first hidden representation of this neural network. And you can see that initially in training for the first 1,000 steps of SGD, these representations are very much Gaussian, right? There's not much going on here. But then after 1,000 steps of SGD, there's some sudden transition that's going on, and all of a sudden these representations become very non-Gaussian. And this is really a key transition in the life of the network, because if I look at the first layer convolutional filters at step 100, so when the kurtosis is still pretty low, you see it's still this sort of scrambled mess. But if I look again after 10,000 steps, so when the kurtosis has gone up, so just after the transition, I can already see the seeds of these Gabor filters, right? So these convolutional filters here now, they have some orientation, they're bandwidth selective, some of them are localized. So what I'm trying to argue here is that really the simple toy model and these deep networks on ImageNet, they do a very similar thing. At a certain point in training, they realize there is something interesting going on in the non-Gaussian statistics of my data, and then they just go. And they just go for them, and they kind of maximize the non-Gaussianity of their projections. And this is not just important for receptive field formation. If I now show you the performance of these three networks from the same runs, you can again see that more or less around 1,000 SUD steps. So when the representations start to become very non-Gaussian, this is where the top one accuracy of these networks actually goes from random guessing towards something that's reasonable. So in other words, I think there's a pattern here where if you want to understand sort of what kind of features the neural networks learn, we really need to look at sort of what you get from looking for these very non-Gaussian projections of your data. Are there any questions on this?
I guess I was wondering if you have any intuition for what starts this onset of starting to prefer non-Gaussian directions?
That's a very good question. I don't have a precise answer for that. I think the key thing here is that you're doing gradient descent, you're kind of trying to minimize your loss, and you'll minimize this loss much more if you actually take these non-Gaussian correlations into account, right? We saw that the final accuracies are much higher if you're training on the non-Gaussian data compared to the Gaussian data. So I guess there's just a strong gradient that goes down that direction. Now, what makes you sort of escape this initial Gaussian phase, and can you speed that up? I don't know. But
Yeah, okay.
it's an interesting question. Any other questions? Okay, so now I've shown you kind of what, our current hunch of what is shaping those representations. Like, what's the mechanism here? Okay, you're looking for non-Gaussian projections of your data, at least in this first layer. But what can you actually learn from that? This is my last slide, my last result. So let's go back to this model of images that we had. Let's do again sort of the expansion of the gradient flow that I showed you in the beginning, which is a nice technique. And I told you that in the Gaussian case, what the network was doing is essentially PCA. So essentially what the network was doing there is looking for some principal components which help it classify these images. Now, PCA is just sort of an eigenvector decomposition of the covariance of the inputs, right? So what we can do here is we can look at this first sort of non-Gaussian term in orange. There's a fourth order cumulant that appears in this non-Gaussian term. So let's just decompose it in a way that's similar to PCA. Okay, so let's do tensor PCA. Let's basically do a low rank reconstruction of this tensor. There's different ways of how you could go about this here, because it's a symmetric tensor. What we did was this perfect decomposition. So in this case, the eigenvectors of the tensors are called CP factors. Okay. So we did this numerically. We sampled the data set from the non-Gaussian distribution. We computed the empirical four-fold cumulant, and then we used TensorLi to compute these eigenvectors, these CP factors. And this is what they look like. So if you have very blurry images, if the images are only slightly non-Gaussian, okay, the edges are not very sharp, or if you have little amount of data, the CP factors are a bit all over the place, right? They are oscillating essentially. There's no particular structure that you can distinguish here, at least I don't see any. And similarly, the weight of the neuron that we're training on this noise versus structure task, it's kind of all over the place, right? This is what I'm showing you in blue. But if I now increase the non-Gaussianity of my data, so if I now make the edges sharper, and hence the relative importance of these non-Gaussian fluctuations bigger, there's a kind of very sharp transition that occurs. And all of a sudden, these CP factors localize in space. Okay, so here I'm again plotting the top 10 leading eigenvectors or CP factors of this tensor. And you can see that they are now neatly localized in space, right? And this is relevant because as the CP factors localize, so does the weight. Right, I'm showing you again the weight at the end of training of this neuron in blue, and it's also localized, right? It kind of converged to one of those CP factors. And so, in other words, the representations that you learn here from these in this very simple model of data, they really are the principal components of these higher order cumulants, which in turn are localized because of the translation invariance that we impose on our images. Like if you look at the paper, we show that, for example, the width of these bumps in the CP factors, it's really proportional to the correlation length of the images. This transition is also fairly yeah, interesting in and of itself. To me, it looks a little bit like, for those of you who like random matrix theory, like a PPP transition for random covariance matrices, right? So here I'm again plotting this localization measure, this IPR, which tells you how localized this is a vector, right? It's big if it's localized, as a function of the size of the training set as I increase, from which I compute this cumulant. And you can see that as I increase the input dimension, there is this sort of transition from a regime in which there's no localization. So in other words, you cannot detect that this data is non-Gaussian, to a regime in which it's actually very localized. And yeah, this is something I'd like to understand a bit better. What kind of transition is going on here? How can we describe that mathematically? But it's kind of a tough problem. Okay, so with this, let me conclude. So the question that we started from was this question of, okay, what do neural networks actually learn from their data, right? What are the statistical patterns in the training data that get picked up by the neural network and shape its features? And so what I tried to argue is that the higher order features, higher order statistics in the inputs really seem to be key to understand this process, seem to be key to understand what kind of features does a neural network learn from its data. But this is daunting in a sense, but there is some hope, right? Because there is some ordering to how the neural networks learns about these higher order correlations, right? So I showed you some examples in the beginning of how neural networks really seem to be learning distributions of increasing complexity through time. And neural networks seem to be good at that. They seem to be learning about these higher order correlations pretty efficiently, both compared to fundamental statistical bounds and to linearized neural networks, random features, the NTK and whatnot. And then finally, what I touched on at the end here is that I think there's a very interesting interplay to understand feature learning, where you start from the symmetries of your data, right? In our simple model of data, of images, this was the translation invariance. You look at how this shapes the principal components of the higher order correlations, right? Here, the translation invariance, it gave rise to this localization of the CP factors with a certain width, which is related to the correlation length. And then you can go from those CPE components, these eigenvectors of the cumulants, to the neural representations, which at least in this simple model were very closely aligned. And I think, thinking along those lines, there's many interesting questions that you can ask. You could look at different symmetries, how they affect the higher order correlations, but you could also ask, what are the symmetries in very different data modalities, right? So for example, what are the underlying symmetries in text? I have no clue. With this, let me thank my collaborators, Lorenzo Bardone, who worked on the analysis of the hypothesis tests, Federica Gerace, who helped us analyze the random features, trained on this model, Alessandro Laio and Riccardo Rende helped us with our collaborators on the transformer project, Alessandro Ingrosso and Maria Finetti. We studied the distributions for increasing complexity and the simple model for images together, and Esther ran the analysis of random features and neural networks on the spiked cumulant model. And yeah, with this, thank you very much for your attention. And I'm looking forward to answering some more questions. Thank you.
Thank you so much, Sebastian. I'm gonna stop the recording now.
Yes,
and
maybe let me
then-
add that Federico Becker and Luciano here, who on the slide, they participated in another project on transformers and quantum physics that I didn't manage to fit in anymore, but I still kept them on the slide.